Good morning, everyone. Welcome to Calculus 3. Hope you're having a great day so far and you're ready to learn some cool stuff from Calculus 3. And good morning to Mrs. Davies. Thank you so much for being here. I appreciate you taking care of everyone while I'm gone. When this class begins around 10:30 a.m., I will be walking around the streets of Jerusalem, and it's about 6:30 p.m. in Jerusalem when this class begins. So a different sky over there, a different perspective. But again, thank you for being adaptable to this video lecture. I appreciate you all very, very much. So we are looking at section 13.8 today. You know it's coming, right? You just learned on Tuesday how to find the equation of a plane tangent to a surface. And there at the end of class, we looked at finding the equation of a horizontal tangent plane. That should remind you of some important things in Calculus 1. In Calculus 1, if you can figure out where there is a horizontal tangent line, you get really important information about the function. You can determine where is the maximum or the top of a hill for a function, where is a minimum or the very bottom of a valley for a function. We're going to do that same skill, but we're applying it to surfaces as opposed to curves in the plane. So what you know from Calculus 1 will be very beneficial today. The process will be similar. In fact, we're going to be looking at a process that is similar to the second derivative test from Calculus 1. Don't worry if you're rusty. We're going to review that information as we go. So let's talk about relative extrema. Let's consider the surface, this yellow-colored surface that we're looking at, and observe where the extreme values are. We have local maxima, we have local minima, we have absolute maximums, we have absolute minimums. So if I look at this point, that would be an example of an absolute maximum because it is the highest point on the graph. This point to the left here, we would consider that a local maximum because even though it's not the highest point on the graph, it is higher than the points local to it or relative to it. We have a local minimum here, lower than the points around it. This one is also classified as a local minimum because I can imagine this surface is continuing to decrease down below that local minimum. So the same way that we define relative extreme values in Calculus 1 for a curve in the plane, we have similar definitions for a surface passing through R3. So number one, the function z equals f of x and y has a relative minimum at domain point AB. Remember, xy ordered pair, that's a point from the domain. The z value is from the range. If f of x and y, notice this is any general z value. It's any z value on that function. So the function has a minimum at this domain point AB if the general z value is greater than or equal to this specific z value. Remember, the upside down A means for all ordered pairs AB in the domain. Let me read it one more time. The function z equals f of x and y has a relative minimum at domain point AB if the general z values, f of x and y, are greater than or equal to this one specific z value, f of AB, for all points A, B in the domain. So basically it's saying the z value of this specific point is lower than the z values local to it. Let's look at a parallel definition. Number two, the function z equals f of x and y has a relative maximum at domain point AB if the general function value, the general elevation z, is less than or equal to the specific z value at this point, f of AB. Notice we're evaluating the function at AB, so that's one specific point, for all ordered pairs AB in the domain D. So in layman's terms, a relative minimum is lower than most of the points around it. A relative maximum is higher than most of the points around it. If we want to get specific, an absolute maximum is the highest point on the graph, and an absolute minimum is the lowest point on the graph. Those should be familiar concepts because you learned them in the plane for Calculus 1. We get one interesting thing that happens, and this is really fascinating. This is something that can happen in R3 that is impossible in R2. So observe the surface over here on the left. Do you recognize that surface? Can you name this surface? Do observe it is a quadric surface. So of the 6 quadric surfaces we studied, which one is this? I hope you said Pringles so that you impress Mrs. Davies. This is a Pringle. This is a saddle. More specifically, this is a hyperbolic paraboloid, right? So let's consider this point right here in the middle, which appears to be at the origin. If I slice it in one direction, specifically parallel to the xz plane, the trace here would be a parabola that opens up. That parabola has a minimum value at the vertex. If I slice it parallel to the yz plane, notice the cross section there would be a parabola that opens down. The vertex of that parabola is the maximum. So the amazing thing about this point right here is that it is a simultaneous maximum and minimum point. It is the lowest point in one direction. If I think about this as terrain and I'm hiking around the terrain, that's going to be the lowest point of my hike in this direction. However, it's going to be the highest point of my hike if I'm hiking up in this direction. So we call that a saddle point. Think about the very center point on a cowboy's saddle. It is the highest point considering how your legs wrap around the saddle, but it is the lowest point front to back. So a saddle point is a simultaneous maximum and minimum. That is impossible in R2. If I'm looking at a curve in the plane, points are either maximum points or minimum points, but never simultaneous maximum and minimum. Those occur on hyperbolic paraboloids and other types of surfaces that we'll examine. So in this section, we're going to be looking at how do I find a local maximum, a local minimum, and a saddle point. We're going to use a familiar term, locating critical points. We're going to relate this to what you know about curves in the plane from Calculus 1 and parallel it with the new technique that we'll do for surfaces in R3. So recall, from single variable functions, relative extrema occur at critical points. What's the definition of a critical point? A critical point occurs where the derivative f prime of x is equal to 0 or where the derivative is undefined. Not all critical points lead to a relative extreme value. So if I consider some curves in the plane, this will be the foundation for what we learned today. Let's suppose I have a curve, maybe a polynomial function, that looks something like this. We'll call this y equals f of x. If we are interested in analytically determining where the maximum and minimum occur, we would calculate these 2 points. Notice at each of these points, the tangent line is horizontal. So whatever the x value is here, we would know that the slope of this tangent line, f prime of a, is equal to 0. Similarly, whatever the x value is for this point, the value of the derivative at that point is 0. So if we find a location where the derivative is equal to 0, it is very likely to cause either a maximum or a minimum. However, not all critical points lead to a relative extreme value. Let me give you an example of this. So let's consider a different curve in the plane. Let's take another cubic polynomial, but one that's not so pronounced. Maybe one that does something like this. We would discover, if I had the equation of this function, let's call it g of x, that at this point, g prime of x would also be 0. There's a horizontal tangent line here. However, it is neither a maximum nor a minimum. Whatever that x value happens to be is still a critical point, but it does not indicate a max or a min. So the first thing that we're going to learn how to do is find all of the critical points. We're going to get a set of potential locations for extreme values, but we are going to have to test each one of those values to see if they do in fact lead to a maximum or a minimum. So let's learn how to find a critical point for a surface in R3. Definition. The point AB, notice it is an ordered pair. It is an ordered pair from the domain. The domain of a surface is two-dimensional, so the domain is a space or a region in the plane. It is not an interval. So domain points consist of ordered pairs AB. So the point AB is a critical point of the surface z equals f of x and y if one of the following is true. Number one, f sub x evaluated at AB is equal to 0 and f sub y evaluated at AB is equal to 0. Now pause for just a minute and think about the geometric interpretations of those derivatives. When we find f sub x, we are calculating the slope of the surface in the positive x direction. And we are discovering if we face east, for example, the slope is 0. F sub y evaluated at a particular point gives me the slope of the surface in the positive y direction. Again, if I imagine myself standing on a surface, I would be looking north. The slope in that direction is 0. Now remember, the directional derivative is a weighted average between those two slopes. What's the slope in the east direction? What's the slope in the north direction? If both of those slopes are 0, then every weighted average of slopes between those two would also have to be 0. So looking at just those two first derivatives, if they are both simultaneously 0, then the slope in every direction would also have to be 0 if we are dealing with a continuous surface, and that is all that we will be dealing with in this section. So what I'm going to do is take the first partial with respect to x and set it equal to 0, and the first partial with respect to y and set it equal to 0. I will solve for the ordered pairs. The results of that algebra will be our critical points, okay? But just like we said in the plane, if my derivative is undefined, then we can also find a possible extreme value. I'm realizing I forgot to include something up here. Let me backtrack for just a minute. If my tangent line is vertical, I'm just going to invert that curve g of x. Let's call this one h of x. If my tangent line is vertical, h prime of x is undefined. Okay, so that takes care of that requirement right there. Okay, so we're going to look at this also as part of our search for critical points for the surface. If we have f sub x of AB or f sub y of AB undefined, then we would also consider that as a possible critical point. Okay? Relating this to the directional derivative, if del f of AB, which is equal to a linear combination of I and j, just a new perspective. Remember, this is equivalent to f sub x of AB, f sub y of AB, angle bracket notation. If the gradient is equal to 0, notice that is the 0 vector, then every directional derivative must also be 0. So again, if the slope in the east direction is 0, the slope in the north direction is 0, and we were looking at a continuous surface, then every direction will have a slope of 0. If every direction has a slope of 0, then the plane tangent to the surface at that point will be horizontal. Okay? So at this point, what you should understand, we are going to be finding critical points first. Those will be the only locations where we will search for maximums, minimums, or saddle points. So example 1, find the critical points for f of x and y equals x to the fourth plus 2y squared minus 4xy. So to find critical points, we're going to determine where are the derivatives equal to 0 or undefined. So let's go ahead and find our partials. The derivative with respect to x would be 4x cubed minus 4y. And we're going to set that equal to 0 and see what information we could obtain. At this point, I can factor out the greatest common factor of 4. leaving behind x cubed minus y. Let's go ahead and divide both sides by 4, just to simplify our equation. And notice I can't really get any information out of this equation at this point. I can't get specific values. I've got an infinite number of ordered pairs that would solve this equation, so I'm going to need another equation to get specific points. That is going to be obtained from f sub y. So we found our first derivative with respect to x and we set it equal to 0. Now we're finding our first derivative with respect to y, which would be 4y minus 4x. And we set that equal to 0. Let's go ahead and factor out this 4 again. Divide both sides by 4. I have another 2-variable equation. We could call that x equals y. So we took both of our first partials, set them equal to 0, and this created a system of algebraic equations. So my next goal is to solve this system of algebraic equations for ordered pairs. We can do this very easily by substitution. By the way, at this point, you will be most likely dealing with a nonlinear system. So one of the best ways to solve a nonlinear system is by substitution. So I notice over here that x is equal to y. So I'm going to use that information and plug x in for y in this first equation. So when we substitute, we would end up with x equals x cubed. That is a 1-variable equation, and I should be able to solve it for x. Let's subtract x from both sides. This is a higher degree polynomial equation that we could solve by factoring. Notice the GCF there is x, so we'll factor that out. And observe we have the difference of 2 squares left behind, which we could factor x plus 1, x minus 1. So we get 3 roots, x equals 0, x equals negative 1, and x equals 1. But remember, our critical points are ordered pairs. So with each of those x values, I only have half of an ordered pair. I have to find their corresponding y values. So I'm going to use back substitution to figure out what y is. Notice this equation will be really simple to generate the y values. When x is equal to 0, y is also equal to 0. When x is negative 1, y is negative 1, and when x is 1, y is 1. So we have 3 critical points. Let's go ahead and list them as ordered pairs. They are 0, 0, negative 1, and 1, 1. So if this surface has a relative maximum or a relative minimum or a saddle point, it will be located at one of those 3 critical points. I don't have to search any other place on that surface, only those 3 points. But keep in mind, at this point, we don't know which one's a maximum, which one's a minimum, which one's a saddle point. We're going to have to do some further analysis to figure that out. All we know at this point is potential relative extreme values. So we'll learn the second partial derivative test to figure out which one is a max, which one is a min, or maybe neither or none of those points lead to a relative extreme value at all. Okay? So to find critical points, find both of your first derivatives, set them equal to 0, solve the resulting system of equations, which is generally nonlinear, solve by substitution, and make sure you express your critical points as ordered pairs. Those are the potential locations for the extreme values. So how do we determine what the extreme values are? Part B, we're going to use the second derivative test. I'm going to call this the second partial derivative test to distinguish it from the second derivative test that you learned in Calculus 1. Let's make sure we remember the details of the second derivative test that you learned in Calculus 1 because we're going to build on that foundation. Before we talk about the second derivative test, think through the first derivative test. Remember in Calculus 1 making all of those sign graphs? Where is the derivative positive? Where is it negative? Where does the derivative change from positive to negative so that you can identify relative maximums or minimums with the correct details? That was a very tedious way of finding extreme values. Then you learn something called the second derivative test. Now I'm not talking about looking at concavity. I'm talking about the second derivative test for extreme values. you can use the second derivative to identify a maximum or a minimum. So let's make sure we remember the details of that test. Recall from single variable functions. Now remember, single variable functions mean single independent variables. So we're talking about curves in the plane as described by y equals f of x. If f prime of c equals 0, now pause right there for a minute. I have my first derivative evaluated at a specific number c and it's equal to 0. What does that say about c? This is code for c is a critical point. Okay, so that means I have found my first derivative, I set it equal to 0, I solved the resulting equation, and the answer was c. So c is a critical point. I then take that critical point and I plug it into my second derivative. If my second derivative is negative, what does that say about the shape of the curve? Is a negative second derivative concave up or concave down? Concave down, right? So if I am located at a critical point, which is a potential max or a min, and I discover that the curve is concave down because the second derivative is negative, then there exists a relative maximum at x equals c. Okay, if I were in your presence, I would be doing all kinds of hand motions. So the best I'm going to do here is draw a picture. If we're at a critical point and the curve is concave down, think about holding your hand down in a cup shape. Concave down means we have a maximum. So sometimes our brains don't want this to work out that way, because when we hear negative, we think minimum, okay? But a negative second derivative means concave down. That indicates a max. So at a critical point, a negative second derivative indicates a maximum. Hopefully you remember that from Calculus 1. Similarly, if f prime of c equals 0, that means I'm still at a critical point, and I discover the second derivative is positive, what does that say about the shape of the curve? That tells me it's a concave up curve, and if we are at a critical point in combination with a concave up curve, that means that that particular critical point is a minimum. So there exists a relative minimum at x equals c. Okay, so hopefully that's familiar to you. You might be a little rusty. That's okay. That's why we're reviewing. But a negative second derivative at a critical point indicates a maximum. A positive second derivative at a critical point indicates a minimum. There was one other thing that could happen. I could take my critical point and plug it into the second derivative and discover the second derivative is equal to 0. Then we say the test is inconclusive. Okay, we got nothing from that point. We would have to resort to some other sort of test. Okay, if we understand the second derivative test from Calculus 1, the details will be similar to our second partial derivative test. So let's get back to our surfaces. Remember, we're looking for maximums or minimums for our surface. Let z equal to f of x, y have continuous second partial derivatives on an open disk centered at AB. What that means is I'm just searching a local area for a maximum. I'm not looking at the entire domain for absolute max and min, okay? Where f sub x of AB equals f sub y of AB equals 0. This is code for I found both of my first derivatives, I set them equal to 0, and solved the system and discovered AB ordered pair is a solution, so AB then is a critical point. Okay, so we're saying we did all this work that we practiced up here at the top. Okay, we set our derivatives equal to 0, we solved the system, and we got some ordered pairs. Those are critical points. Let big D of x and y, so D is a specific function that we're going to form from our second partial derivatives. So let big D of xy equal f sub xx times f sub yy minus f sub xy squared. Remember, we are dealing with two independent variable functions, so we have a lot of second derivatives. We are no longer in the days where we have a single unique second derivative. We have 4 second derivatives, 3 of them are distinct. We have the second derivative with respect to x. That means I differentiate with respect to x twice. Here we differentiate with respect to y twice. And here we have a mixed partial, and don't forget f sub xy is equal to f sub yx. Okay, so you could think of that last term as the product of your mixed partials, or pick one of them. They're going to be the same thing, f sub xy squared. So I'm going to find all of my second derivatives, and I'm going to form this, what I'm calling a test statistic. Okay, I'm going to test this function for its sign. So I find my second derivatives, I form this function, and then I've got 4 conditions. Number 1, if I take my critical point AB and I plug it into the function that we just formed, and we discover that D is greater than 0, okay, a positive function D, and the second derivative with respect to x is positive, there exists a relative, anyone want to take a guess? Maximum or minimum? Look, positive second derivative. What did a positive second derivative tell me up here? Positive second derivative went with minimum. Positive second derivative here also goes with minimum. Okay, try and relate it back to what you know. Number 2, if D of AB is positive, that's the same as the first case. But this time I find out that my second derivative with respect to x is negative. Now pause for a minute. What did a negative second derivative tell us above? That we were dealing with a maximum. So a negative second derivative in this case also is a maximum. Okay, so I'm going to find D. I'm going to plug in my critical value. If D is positive, I'm also going to check the sign of the second derivative. A positive second derivative indicates a minimum. A negative second derivative indicates a maximum. Another thing can happen. If we find D of AB is negative, I don't have to check anything else. If this guy D is negative, there exists a saddle point at AB. That's one of those simultaneous maximums and minimums. A maximum in one direction, a minimum in the other direction. Finally, like the second derivative test from Calculus 1, if the value of D is 0, the test is inconclusive. We would have to resort to another method for locating maximums and minimums. Note, the test relies on the quantity big D of x and y, which is also called the discriminant. See if I can spell it right. It can also be remembered as a 2x2 determinant of what's called the Hessian matrix. This Hessian matrix simply contains all of your second derivatives in matrix form. So think about finding the 2x2 determinant of that matrix. That would also give us this function D. The condition that D is positive from our first 2 conditions implies that the surface has the same general behavior in all directions. Near AB, either the surface rises in all directions or it falls in all directions. That's how we can make the conclusion of the max and min there. Okay, let's get back to the surface we were considering in example 1. We found that this function f of x and y has critical points 0, 0, -1, -1, and 1, 1. We found that by setting our first partials equal to 0 and solving the resulting system. Now we want to figure out, do any of those points give us max, min, or saddle point? So we're going to use the second partials test to identify the relative extrema or saddle points of f. Express these points as ordered triples. Okay, we've got the domain points. That means we have x and y. Eventually, we'll find the corresponding z values. So what we need to do is build this function D. So from our definition, D of xy is equal to f sub xx of xy, f sub yy of xy, minus f sub xy squared of xy. So before I can do anything, I better get to differentiating. Recall our first derivative with respect to x was 4x cubed minus 4y. So I'm going to use that to find second derivative with respect to x. We would end up with 12x squared. Let's go ahead and find f sub xy at this point. So I'm looking at my f sub x, this time differentiating with respect to y. We would end up with -4. Let's find f sub y. In fact, we already found f sub y. We have obtained 4y minus 4x. That was from our previous work. If we differentiate again with respect to y, that gives us 4yy. The derivative there is 4. And just to check our work, let's go ahead and find f sub yx. So I'm looking at f sub y, differentiating with respect to x. What would we obtain? Notice these two should always be the same when we're working on a continuous function, and that is a great way to check our work. Okay, so we have all of our second derivatives. Therefore, our function d of xy equals f sub xx, we discovered that was 12x squared, times f sub yy, that's equal to 4, minus our mixed partial squared. So when we simplify, we get 48x squared minus 16. This function is going to help me determine which of our critical points is a max, min, or saddle point. Okay? So I'm going to organize this information in a table. Let's list our critical points. We have 3 of them. We're going to need the value of this function d of xy. We also need to check the value of our second derivative, which, by the way, you can also use f sub yy right there. You can use either one, f sub xx or f sub yy. Use either one of your pure partials, pure second partials. And then we can identify what's the type of the point. So the first critical point we found was 0, 0. So I'm going to look at my function, 48x squared minus 16. This one happens to just depend on x alone. Sometimes you'll have both x and y there. If I plug in x equals 0, we would discover the value of the function is negative. If I'm looking at my 4 conditions as listed up here, if that d is negative, we don't have to check anything further. We have a saddle point. So we can skip this part and make our conclusion this is a saddle point. Okay? The next critical point we had was negative 1, negative 1. If we plug that into our function d, now we don't necessarily care about the value, we just care about the sign, we would discover d is positive. Now, since d is positive, I also have to check the sign of the second derivative. You can check either f sub xx or f sub yy. So if I take x equals negative 1, y equals negative 1, plug it into my second derivative, we discover the second derivative is positive. A positive second derivative indicates a relative minimum. The last critical point we had to check was critical point 1, 1. First, we plug it into our function d. We would discover the value of d is positive. Since the value of d is positive according to the test, we also have to check the sign of our second derivative. When we plug it into our second derivative, again, we find it is positive. Therefore, our conclusion is relative minimum. Okay, it's going to take some time to sit down and memorize the details of that test. Please relate it to what you already know from Calculus 1. It will make it much easier. So our official report is that there is a saddle point at ordered triple, x equals 0, y equals 0. We need to find the corresponding z value. So we're going to go back to our original function. We're going to plug in x equals 0, y equals 0, solve for z. We would discover z is also 0. So there is a saddle point at 0, 0, 0. We found 2 relative minima at negative 1, negative 1. Again, if I plug x equals negative 1, y equals negative 1 back into the function, we would discover z is also negative 1. And our other critical point was 1, 1. If we plug x equals 1, y equals 1, z value there is also negative 1. Okay? So we have a saddle point at the origin, relative minima at those 2 ordered triples. Okay, so again, relate it to what you know from Calculus 1. It sure is helpful for learning this new test. So can you imagine the shape, the possible shape of that surface? We have minima at 1, 1, negative 1, negative 1, negative 1, negative 1, and a saddle point in the middle. So what would happen there is kind of a cross section here. You'd have a minimum at 2 of those points in one direction. So here would be our 2 minima. This guy would be a saddle point. Notice it's a maximum in this direction, so we would have another part of the surface looking front and back going like so, okay? So imagine your minimums this direction, minimums this direction. This one would be a saddle point because be a minimum this direction, maximum that direction. So you have this hilly, interesting spot in the middle of your terrain. Okay, let's try it again. Example 2. Find the relative extrema or saddle points for the function f of x and y equals big square root function. All right, we've got a big square root function. We have a lot of quadratic terms there, so it's probably going to be a quadric surface. Let's describe which part of the quadric surface is represented by f of xy. If we change our function notation to variable notation, then we'll be able to manipulate this algebraically until we recognize the surface. So square both sides. That gets rid of our radical. Let's move all of our quadratic terms together on one side. Let's see, let's move the z to the right. Okay, I'm going to rearrange as we go. I'm going to get the x's together. Next we'll have our y term, our z term that we've moved over from the other side, which should be minus z squared, and then this constant 5. We can complete the square in x to recognize a transformation. If we complete the square in x, we divide this coefficient negative 4 by 2 and square it to get 4. But since we added 4, we need to subtract it off to keep our equation balanced. And then we can factor with respect to x. We'd have x minus 2 quantity squared plus y squared minus z squared plus 1. Okay? Actually, we need the entire thing equal to 1 if we're determining which quadric surface it is. So let's move all of our squared terms to the left. We would end up with z squared minus y squared minus x minus 2 squared equals 1. So that is the standard form for one of our quadric surfaces. Notice all of our terms are quadratic, but 2 of them have different signs, and it is equal to 1. So this would be a hyperboloid of 2 sheets. The hyperboloid of 2 sheets shows a transformation in the x direction. So the center of this hyperboloid of 2 sheets would be x equals 2, y equals 0, z equals 0. Okay, so again, this is a hyperboloid of 2 sheets. But if we consider the original function, if we were to reverse all of our algebraic steps and solve for z, we recognize z is equal to the positive square root, which means we're only dealing with the top half. So if we were to imagine a graph, we have an upper portion of our hyperboloid of 2 sheets. We have a lower portion. I'm just going to draw this with dashes because we're not actually going to consider that. We're only going to consider the upper half, or the part where z is equal to a positive number. Okay? There is a translation on the x-axis. I didn't indicate that very well on the graph, but we've discovered if the center is 2, 0, 0, then this vertex would be 2, 0, 1. Okay? Remember, we look below the z, take the square root of that number to find the distance between the center to the vertex in the z direction. So we can, based on what we know about graphing, predict that this function is going to have a relative minimum at 2, 0, 1. Okay? So we know the answer ahead of time. Let's see if we can determine that analytically. Shortcut, the entire surface will have the same critical points as the partial surface, but the general surface is easier to work with algebraically. What that means is if you consider having to find the derivative of the original function with all of those with the radical, you'd have some chain rule issues to deal with. You'd have complicated looking first derivatives. So what we're going to recognize is that if I maximize or minimize the radicand only, I will still be maximizing or minimizing the square root function. So we can say, let's go with g equal radicand only. If I can maximize or minimize g, then I have also maximized or minimized that radical function. So let's go through our second partials test. First, we're going to need all of our derivatives. So we find the partial with respect to x. That gives me 2x minus 4. The second partial with respect to x would be 2. The first partial with respect to y is 2y. And the second partial with respect to y is 2. Okay, let's get our mixed partials. Working again with g sub x. This time, if we differentiate g sub x with respect to y, we obtain 0. And just to check our work, let's look at g sub y and differentiate with respect to x. Again, we would get 0. So we feel pretty confident based on those results that we have our derivatives correct. Let's find our function d of x and y. We have f sub xx times f sub yy minus f sub xy squared. So f sub xx is 2, f sub yy also 2, and f sub xy squared. So in this case, very interesting, our function d is always positive. So that indicates we're only going to be considering those first two cases of our second partials test. Okay? Now, before we can run the second partials test, let's go ahead and find our critical points. So our critical points are obtained from setting our derivatives equal to 0. This one works out really nicely. If I set g sub x equal to 0, notice we'll be able to solve that one directly without having to solve a system of equations. And if we set g sub y equal to 0, we automatically get a solution there. So our only critical point we need to consider is 0, 0. I'm sorry, 2, 0. X is 2, y is 0. D of 2, 0 is positive. Since d is positive, we also consider the value of our second derivative. Notice our second derivative is always also positive. So a positive second derivative indicates that we are dealing with a minimum. So there exists a minimum at domain point 2, 0. Let's express this as an ordered triple. If x is 2 and y is 0, and I want to find the corresponding z value, now I'm going to go all the way back to my original function. I'm going to plug in x equals 2, y equals 0. What would we end up with? Let's see, if x is 2, we'd have 4 plus 0 minus 4 times 2 plus 5. So 4 minus 8 is negative 3. Negative 3 plus 5 gives me 2. So we end up with square root of 2. Okay, sorry about that. Had to pause. I knew something was wrong. I can't calculate. 4 minus 8 is negative 4. Negative 4 plus 5 is 1, and the square root of 1 is 1. Thank goodness, because remember, we predicted the point 2, 0, 1. So 2, 0, 1 is a relative minimum. So what we're seeing is that our graphing skills are lining up now with our analytical skills. We can use our intuition to figure out or predict where we think that minimum might be, and we have verified it analytically. Also notice on this problem, finding your critical points was a very easy process. Sometimes it is a very easy process. Other times the algebra gets pretty challenging. Now let's look at just a couple of applications. What I want to do on both of these examples is help you to set up your function, but the second partials test works out in a very straightforward way, and since we've already done 2 examples of that, this is just to assist you to get started with the applications on your homework. Okay, so we're going to do at least the setup for these 2 problems. Example 3, a shipping company handles rectangular boxes provided that the sum of the height and the girth of the box does not exceed 96 inches. The girth is the perimeter of the smallest side of the box. So if you want to send something in the mail, your package has to fit within these parameters. Our goal is to find the dimensions of the box that meets this condition and has the largest volume. So we have a box we could represent as a rectangular prism. This box has dimensions, let's call them X, Y, and Z. You can call it length, width, and height. Whatever you want to do is fine. Now, the restrictions here says that the girth of the box, which is the perimeter of the smallest side of the box, cannot exceed 96 inches. Okay? So the sum of the height and the girth of the box does not exceed 96 inches. Let's assume that Z is the height and that the smallest perimeter would be X plus Y. So we want to make sure the height plus the girth is 96 or less. The height of the box is Z. The girth is the perimeter of the smallest side. The perimeter of our base there is 2x plus 2y. We need to make sure that stays within 96. Now let's go ahead and isolate the height. The height Z will be 96 minus 2x minus 2y. What is it that we are trying to maximize? The problem says we want the biggest possible box, the largest possible volume, so we can pack it with the most amount of stuff, but still stay within these parameters. So let's write a function describing the volume of this box. Of course, the volume of a rectangular prism is x times y times z, length times width times height. The problem with this function is that I cannot run the second partials test on it as it stands because I've got 3 variables. We've learned the second partials test with respect to 2 variables only. So I need to reduce the number of variables from 3 to 2. So what we're going to do is replace the z value with what we found over here, which will also encode the restrictions for the girth into our function to be maximized. So we'll reduce the number of variables here. Volume dependent on x and y is x times y times 96 minus 2x minus 2y. Okay, so this is the function to be maximized. That is the hardest part of the problem. Once you get it set up, you find your critical points. And then run your second partials test. Okay, and then you'll be able to determine the dimensions of the box that maximize the volume but still lay within those particular conditions. Okay, so I'm going to do a dot, dot, dot on this. You can set the problems up on your homework and run the second partials test. Let's look at another example that we're going to set up. Find the point on the plane x plus y plus z nearest the point 0, 3, 6. So we have a plane passing through R3. We have another point in space, 0, 3, 6, and we want to minimize the distance between the point P and the plane that's given there. You could certainly use vectors to solve this, or you could use our new second partials test because we are trying to minimize distance. So what we want to do is start out with any general point on this plane. So any point on the plane could be described by ordered pair x, y. Now I don't want to use z because I'm avoiding 3 variables. I really want just 2 variables. So I'm going to solve for z and obtain 4 minus x minus y. So any point on the plane x, y, z could be represented by two variables alone, x, y, 4 minus x minus y. What we want to do is determine the distance of any point on this plane to the given point, 0, 3, 6. In this case, we can use an ordinary distance formula. Let's call it d of x and y. And we're going to find the square root of the sum of the squares of the differences between all of those components. So we would take first component of my first point x minus first component of the given point 0 and square it, plus the difference between our y components squared and the difference between our x components squared. Okay? If we simplify that, we end up with x squared plus y minus 3 squared plus negative x minus y minus 2 squared. So we have a two-variable function that we need to minimize. Do observe we are dealing with another radical function. So if I run the second partials test in this particular format, it's going to be pretty complicated with the derivatives. So this will also be equivalent to minimizing the radicand. We'll call it r equal to x squared plus y minus 3 squared plus that third term. Okay, if I can minimize this function, I'll find the point on the plane nearest the given point. So again, find your critical points, and then run your second partials test. To figure out the point on the plane that is closest to that given point. So the idea of these two examples is to determine a function that has only two variables and then run your second partials test on that. All right, that is it for the week. Thank you for your listening ears and your attention today. Please allow me to wish you all a wonderful and restful and safe fall break, and I'll look forward to seeing you when we come back. Please don't forget, this is a great opportunity to read your Flatland book and to answer those questions. Those questions will be due first thing when we get back from fall break. All right, have a good day. Bye-bye.